Do you guys have any questions before we begin? Yes. So yes, the AI still chooses randomly, but because the seed I use to seed the random number generator is a constant, I get the same behavior every single time. Talk more about randomness today. So back over here to this vector or this sorting that we left off on. So let's say we had the string 25, 17, 35, and 20. So iterator starts at position 0 at the 25, and then we attempt to find the minimum value beginning at 25 going all the way to the end. So which is the smallest? 17. So what we end up doing is we swap 17 into the first spot. So 17 and 25 trade places. So we get 17, 25, 35, 20. Then what we do is now we have to find iterator will have been advanced to be at this position right here, the 25. So now we find the minimum value from among this range, which is the 20. And so now the 25 and the 20 swap spots. So you'd get 17. Oops. You get 17, 20, 35, and then 25. Now iterator advances again from this position to the next position. So now we're at the 35, and we try to find the minimum value between 35 to the end, which is going to be 25, right? So those two swap spots. So we get 17, 20, 25, and then 35. And then we search from 35 to 35. So who's the smallest? 35. So 35 and 35 swap. Does that make sense in terms of how this algorithm works? So for finding the minimum iterator, what do you think that code would look like? So like we're going to get back the iterator that holds the position to that minimum value. Right? Here's the signature down here at the bottom. So what would you do? So you get a place to start searching from, and you get the end, where you want to start at. Yeah. So again, don't think about like where we're starting at. This tells you where to start at. You're starting at here. I tell you, I want you to start here, and I want you to search up until this range. Find me the minimum thing in this range. Right? So I could start you at the beginning. I could start you somewhere in the middle. Right? But here's where you're starting at, from here and then to the end. Yeah. Right? So what we end up doing here is we have our minimum iterator, right? This is the iterator that's pointing to the smallest value. And we assume at the beginning that the smallest iterator, right, the position of the smallest value is at the beginning. So you make it equal to start. Then I go through the elements beginning at start all the way up into the end, right? The normal iterator for loop. And if I find a value that's smaller than the current value we're referencing, I update it. And then once we get through that for loop, we must have found the smallest value so I can return the iterator that's at that position. Any questions here? Yeah. So the for loop, right? This is the standard iterator for loop that you've seen before. For iterator equals the beginning. Iterator doesn't equal the end. Go to the next thing. Right? But notice like start and end are two variables that I've passed in. When I called it back up here in vector sort, I passed in the iterator the position I was currently at in the array. And I said go up to, but not including the end of the vector. Any other questions here? Yes. Because the editor likes to collapse down the templated types up here. So it is, all of these ones are template type name T, where you see that little just triangle T. It's just being hidden because it's like kind of noisy, I guess. So then over here we have another function, contains, again, that checks to see whether the container contains a particular value. So what we do is, again, we use find, and hopefully we'll talk about the algorithm library very soon. So we search from the beginning of the container to the end of the container for the value, and if we don't equal the container's end, this last value, we must have found it somewhere else. So as long as you don't equal the end, we'll have found the value. If we do equal the end, we won't have found the value, and so we won't contain it. Any questions here? Yes? Back here, I use start, but notice that start is a variable that I passed in. At the beginning, right, up here, I pass an iterator, and notice iterator, the very first time, it was equal to the beginning of the vector. So that's why we started searching from 25 all the way to the end, right? But since the iterator gets advanced over here on this line, right, plus plus iterator, next time we do this loop, iterator is going to be at the 25. So we'll search from just this range. The next time we go around, iterator will have again been updated, so we'll be at the 35, so we'll only search this range, and then we search the 35 to 35. Yeah, that's the sorting one. And then over here, right, here we have the specialization of a min for integers, and it just says I'm a special min function just for ints, and then again it just finds the minimum of the values. Do you guys have any questions about templating over here? Because all of these functions we could have written for a particular type, but we wrote them for just in general templated types, right? Nothing in particular. Because wouldn't you agree that regardless of what the vector contains, sorting it is the same? Right? There's no difference, right? If we're sorting a vector of integers versus a vector of doubles versus a vector of shorts versus a vector of strings, right? As long as the less than operator makes sense, sorting is the same. So that's why we're templating here, because we're able to work for all vectors regardless of type, because the code is the same. Yeah. A short is like an integer that can't hold as big as values. So it's like a integer that can only it's an integer value that can only represent like 2 to the 16, whereas an integer can go up to 2 to the 32 minus 1. So over here in main, I'm calling some of these functions. So I make a vector of numbers, and I make a vector of names. So over here, I call this function minPrinter. And so minPrinter is also, oops, where did that go to? So here's minPrinter. All it does is it prints out, right, like the min of A and B equals the min of A and B. But notice again, this printer is templated because I want it to work with both strings and vectors and doubles and whatever else I wanted to do. Right? So here, this would be calling minPrinter. What would our templated type T be here in this case? Int. Here it's very explicitly int, right? And remember, we've specialized the int template for min, so we'll actually print out an additional output like I'm a special int function. Here we're doing it specifically for strings, again, being explicit. This, again, is not necessary. It's just here to show you that you can indeed do it. Just one second. Here we're doing it for doubles. And here, even though these values are integers, right, I said use which one? The double one.
Does it use the special? Or just...
It will use the special int function because we have defined int for it.
If you don't call it, will it?
Yeah, like this one still uses the special int function because the type will have been deduced. Actually, for this one, the string was actually necessary, if I remember correctly. Because if we try to build it now without it, it's like, oh, right? So if we kind of scroll over for this error, it says error, no matching function called to min for const char 6, const char 6. Because technically the type of these aren't strings, they're arrays of characters. And so I had to say, oh, I really want to, and arrays of characters don't have the less than defined on them. So I said, oh, I want to use the min of strings. So what will happen is the character arrays will be converted into strings as they get passed in. and then we don't get any of these like nasty like errors, because you can see they're like fairly long. And it won't complain anymore. So over here for sort and print vector, again, here's my templated types. Notice that in this function, I accept a copy because I didn't want to modify the original after when I was sorting it and printing it. So pay attention to that. So I first print out the vector, and then I sort the vector, and then I print it out again. Some of you may have noticed when you've been doing your homework, can you print out a vector directly like I'm doing? No, but I know some magic, and I'll show you this magic. So this operator over here, this function, is the function that you define if you want to be able to print something to the screen. Or not just to the screen, but to a stream. Which again, this will allow me to write to any O string, which includes files. So the syntax for this function, which again, we'll get more into this later on, is you're going to return an O stream reference. The name of the function is operator arrow arrow. Your first argument will be a reference to an O stream. And then the second type over here will be the type of the thing that you want to print out, whatever that happens to be. So now for this function, I have to say, well, how do I want to print out a vector of t's? Well, what I said to do was go through each of my elements inside the vector and print out that element, followed by a space. Then at the end, you're going to want to return out. So what happens down here, when I do arrow arrow vector here, what actually happens is this function gets called. Because now, right, we're trying to use the outstream operator on a vector, and this is the function that defines how to like what you should do for a vector of type t on an outstream. Operator plus, operator minus, operator times, operator unary negation, right stream operator. Basically, any of the default things that you see, like plus, minus, times, minus, minus, you can overload how that operator behaves for a certain type. We will talk more about operator overloading later on. I just wanted to show you this so that you can use it in your code to help you print out your vectors a little bit easier. We could have just written this as just some plain old function like print vector, right? We could have had this thing just be like print vector to this outstream, right? And then we would have done the exact same thing. But what I'd have to do back here, I wouldn't be able to do like arrow arrow vector. I'd have to say like call print vector, and then it would go and print it out. Operator is a keyword. Yeah, it defines, it's how you specify a function for the behavior of like a particular operator, like operator plus, operator minus, operator times, etc. Yes? You cannot do a triple less than sign. It's for the ones that actually exist in C++. So what actually happens over here is this is like first we evaluate this expression right here, which causes the string starting vector to be printed to the screen, and then this returns cout. So now we have cout arrow arrow vector, right? Which causes us to call this function. We have a outstream operator, cout, and our vector. So then we go print that to cout, and then we return cout again. So now this expression again evaluates to be cout, and then we have cout, and then we do the new line to it. So that prints new line to the screen and then returns cout again. So by returning the operator over here, that's what allows us to chain the operators together, have one followed by the other. So that's just printing for you if you want to borrow that. So sorting and printing, not too interesting, right? We print it out, sort it, print it out again. For contains, again, not super interesting. We, cout value is, and if we don't contain it, we put out the extra word not contained in the value of elements. And I think that covers all of them. So if we go ahead and we run this code, run. Code is built. So you can see here that when I call the min functions, they print out I'm a special min function just for ints, right? Because they're specialized. And then the min of 35 and 8 is 8. And then this one also, again, because it's specialized for integers, also has that extra print statement, which makes things look ugly. We find the min of zebra and apple, it's apple. The min of 35.68, right? That makes sense. The min of 35 and 25 is 25. But again, notice that we called them as doubles, so that works out just fine. Over here, here's our starting vector, 25, blah, 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 blah. After we sort it, that looks pretty sorted to me. Our vector of names, we sort it. After we sort it, right, looks good to me. 55 is contained in here. Hey, look, there it is. 32, nope, he's not in there. Right, Michael is not contained inside these list of names, but Bob is. Do you guys have any questions on templating before we move over into randomness? Okay, let's go talk about randomness then. I know like we're moving like 1,000 miles per hour in this class. That's because we have so much to get through, and I'm on the wrong 5. And I really wish we could go slower, but we just don't have the time to. So after this, you should be able to do your homework assignments. Technically. I mean, at least we'll have covered all the topics in class. So if you want to use the random stuff in C++, you have to include random. C++ splits random into 2 distinct parts. The first part are the random number generators. These are the internal implementations that generate some random sequence of bits or generate some random number. Then there's the distributions. These control what values are generated and how likely a value is to appear. They use the bit string that's generated by the random number generator to produce some value in their range, right? If anybody have to take statistics classes, right? Any of you haven't, you probably have heard some other types of like distributions, like a normal distribution, right? That's like more likely to occur in the middle and less likely to occur at the ends. But then we also have like uniform distributions where every value is likely to occur, like when you roll dice. But there are other types of distributions like exponential distributions and logarithmic distributions and Poisson distributions and chi-squared distributions, right? There are a lot of distributions, but we won't be using most of them. If we want to get a random value, we need both a generator, though, and a distribution. So the first thing about the random number generators is most of them are pseudo-random numbers, which means that they don't really produce real random numbers. They just produce stuff that looks to us like it's random. Because these values aren't actually random, and there is some like algorithm used to generate them, never use these pseudo-random number generators for like any encryption. It's really easy to break it then. If you want true random numbers, you have to use std : random device, but it's not available everywhere, unfortunately. So if you want to get a random number generator, there's 2 different constructors. You say your random number generator or your random number generator with the seed. The first one will use the default value for the seed. The second one will use the specified value for the seed. If you do create a random number generator, you can always explicitly seed it by doing random number generator.seed with the value. When you seed the random number generator, you're going to set its state to be something particular. If it's set to some particular state, it's going to generate some particular sequence of random numbers. If you want to get a random integer from the random number generator, you do RNG parentheses. So here you can see that I make a min std random number generator called RNG1, who's been seeded with the value 5. Here I create another type of random number generator. It's a min twister random number generator called random number generator 2, and then I seed it after creation using 17. If I do RNG1 right now with parentheses, it'll give me some random number. RNG2, some other random number. I don't know really what's going to come out. If you're curious about the list of all the possible generators that exist, sorry, here's the list of the random number generators that you could use to generate values. They all pretty much have the exact same interface to use. So again, the seed, it's used to initialize the state of the random number generator. If it's a known value, like some constant value, it's always going to produce the same set of random numbers. This is extraordinarily useful for when you're testing, because if your code has bugs in it, it's really annoying if those bugs only trigger some of the times based on some of the values, right? If you make it so that the random number generator always gives you back the same values, it's always going to break at exactly the same time, helping you to figure out where the error is at. The way that I like to think about this and explain it, but not release what's happening behind the scenes, is think about that there are many different streams of random numbers that exist, right? And when you seed the random number generator, it picks one of these potential streams of random numbers and sets you at the beginning of the stream. So maybe if I seed my random number generator with the value 20, it puts me at this sequence right here, the second one. So now when I get my first random number, it's going to be 8. If I ask for another random number, it's going to be 1, then 9, then 25, then 99, then negative 65, and so on. If I seed it again with 20, it's going to put me right back here at the beginning. And I'll get 8, 1, 9, and 25, and so on. Does that explanation make sense? And just to be clear, the random number generator doesn't really have this list of numbers stored, right? It uses some algorithm to compute the next number in the sequence. Yeah, so if you seed it with the same state, it's always going to give you that same sequence, that exact same sequence of random numbers. So if you want to be a little bit more random, you can seed the random number generator with the time, right? Because it's very unlikely for people to play at the exact same time. If you wanted to seed it with the time in C style, it'd be time null pointer, which is what you're doing for your homework assignment this time. If you wanted to do it the C++ style, you can see it's a big old mouthful of stuff. But that'll give you the current time as a number. This is what you would do when you were like finally releasing your game or your program out to the public for people to use. Because then they'd get different behavior every single time they played your game or used your program. So for distributions, most of the time you're either going to use a uniform int distribution or a uniform real distribution. Both of these are equally likely to choose a value in their range. There are other types of distributions that exist, but you'll probably never use them when you're programming unless you're doing some statistical simulation. Just won't end up being needed. The uniform integer distribution generates a value between A and B inclusive. The uniform real does inclusive on A, but does not include B. So up to, but not including B. So when you want to create a distribution, either a uniform distribution or a integer distribution, or either a real or a integer real uniform distribution, you say your distribution and then the min and max. What are the minimum max you're willing to produce? And then when you actually want to get a value inside that distribution, pass in the random number generator. And it'll give you a value inside that distribution. So over here, I might create a uniform int distribution. Inside these triangular brackets, you either have to put int or nothing for it to be created. And so now I have a uniform int distribution between 3 and 17. So this one will give me a uniform real distribution. Inside these triangular brackets, you either need to say nothing or double. And this will be between negative 25.36 and 57.89. So here I could create some random number generator that I've seeded with the value 5. If I do int distribution, right, this variable up here, and I pass in the random number generator, I'm going to get some value between 3 and 17. I don't know what, but some value. If I pass in that random number generator to my real distribution, I'm going to get a value between negative 25 and 57.89, but not including 57.89. Okay, any questions before we move on to examples? Yes? Well, like there are more potential values that can be chosen inside of a real distribution than for an integer distribution. But sometimes you need integers, sometimes you need real numbers. Does that make sense? Yes. The seed does not choose which algorithm you use, right? Like in terms of like which generator, right? The type over here determines which generator I'm using. So min std rand, or I could say like I did back here, mt 19937, right? The seed in my example, right, tells us like which of these sequences of numbers to start on, right? But different random number generators produce random values differently. So if you see two different random number generators, like a min std and the min twister random number generator with the same seed, they're going to give you different values back because they generate the random values differently. Any other questions? Yes. Why are there so many different random number generators? So that you can get exactly what you want, I guess. So if like you're really doing like hardcore statistical simulation, you probably really care about what's being done behind the scenes and like how really uniform is that distribution going to be. And so by having these different ones, it gives you much more finer control over what happens behind the scenes. But again, for us, it's probably like this is complete overkill for what we need. Okay, examples then. So the reason that we did templating first was that I templated my code so that it could work with different types of random number generators. So you can see here in main, I create two different random number generators, RNG1 and RNG2. The first one I initialize with the constant seed3. The second one I initialize with the random number generator with the time, so I get different values. So over here, I make a vector of random numbers between 10 and negative 100, and I make 10 numbers between negative 100 and 100 using these two different random number generators, RNG1, RNG2. I print them out. Then I randomly select one of the elements inside of it, print it out, and then I also randomly select some of the elements with each element possibly being picked from multiple times into a vector, and then I print that out. So you can see that if we run it, the one that's been seeded with the constant value is always going to give us the same result every time. So notice this set of numbers is always going to be the same the first time. This set of numbers will be different if I run it again. Same, different. Same, different, right? Because I'm giving the constant seed, so I get the same sequence of values every time. The other one, since I keep running the program at different times, I get different sequence of random numbers. Does that make sense? So that's just for printing. So let's say I wanted to write a function that could just give me a random integer between min and max. So notice this function over here, it's templated over the random number generator type. This would allow me to pass in, min std random number generators, also the min twister random number generators, or any of the other ones that exist. So what would you do inside this function, given you have a min, a max, and a random number generator? And you want to produce a value between min and max. Yeah. So we create a distribution between min and max, and then we use that to get our value. So if we go to it, hey, we create a uniform integer distribution between min and max, and then we use our distribution to get a value from the random, we use the distribution and the random number generator to get a random number inside that distribution. Does this make sense? Yeah. That's the type of the random number generator, right? This is my template type. So right now when I'm calling it, it could potentially be a min std rand, right? But I could also create one of the other types, right? Like std min 1993, like random number generator 3, who maybe has a seed of 85. Right? And so now what I could do is say something like std : cout get random int with, say, between 10 and 13, and I can pass in RNG3. I could also do the exact same thing, but pass in random number generator 1 and maybe, oops, RNG1. And notice the types of these two generators are very different, right? This is a min std rand generator. This one is a MT 199037, whatever, right, generator. And so when I call the function this time, again, we go over to our template type, and we're going to replace RNG type with min rand generator, right? So the first time I call it, I'll replace that function, that type, RNG type, with this guy right here. The second time I call it, I'm going to replace that type with MT 1993.7. Does that make sense? So this allows me to write this function to work with any random number generator, not just a fixed one. It does not randomly choose which random number generator I use, right? I specify which one I want to use, right? But I can work with any random number generator. Any questions here? So let's say I had a container, and what I wanted to do was randomly pick one of the elements inside that container and give an iterator back to that element. That's what this function over here does, select randomly. It randomly picks an element inside the container. The container could be a map, the container could be a vector, the container could be a string, right? I don't really care, because how I pick one is not going to be very different. We're cool here what this function does. So what would you do? Yes? Like what it does? So what it does is it randomly picks an element inside the container and gives you back an iterator to that element.
If you had a map,
So if you had a map, it would give you a pair, or it would give you an iterator to a pair, right? The key value. Yeah. What type of distribution do we want to use? Yeah, uniform integer distribution, right? Yeah, it doesn't print it, but it gives you it back, right? So what I did is more or less that. So the first thing that I do is I ask for a random number between 0 and the size of the container minus 1. That makes sense, right? Because our indices can be between 0 and up to, but not including the size. Are we cool here? The next thing that I do is I make an iterator to the beginning of that container. So I call begin, and then what I do next is I call advance. Advance is a method inside of the iterator header file that moves this iterator this amount. There are different types of iterators. Some of them you can't just do like iterator plus 5. It doesn't always exist. But if it does exist where you can just add some number to it, it will do it, and it'll do it very quickly. If it's not able to just add 5 to it or add how much you want to, it'll call plus plus on it like 5 times in a row. So it will do it the smart way if it's available, the smart fast way if it's available. But if that fast way is not available, it'll default to the slow way. So I move the iterator that amount, and then I return the iterator to that position. Any questions here on randomly selecting something? The only thing I think that's like marginally interesting in this example is the advance. It just says move this iterator this much. The next thing that we have is sample with replacement. which what we do is we pick elements from our container, right, until we finally find something that's, or until we finally get enough of the elements that we want to pick. So we'll talk about this in a second, what the type is over here. So the first thing then that we take in is the container, right? How many samples do we want to take from this container? And then some random number generator to help us pick those things. What we do is we create a vector, and here you're seeing something a little bit new. Container type, : value type. Some of the objects in the STL, and like I should say all the containers in the STL, they have a member called value type, which is the type of the element inside of them. So if I had a vector of ints, my value type for that vector of ints would be int. If I had a vector of strings, value type is going to be string. If I have a vector of doubles, it's going to be double. But inside this templated function, I don't know what you're a container of. Here's a container of something, and I need some way of getting that type, which is the : value type. Now, sometimes this type right here, value type, it depends on containers type, right? Because if container type was like a vector, right, it'd be like a vector of values. But if it was a map, it'd be a map of some value type. This is what's called a dependent type, and the only time I know when the type is dependent is if the compiler complains at me. And if it complains about you about that type being dependent, you stick type name in front of it. And then it stops complaining. So if I get rid of type name here, it should be like, hey, template argument for template type parameter must be a type. Did you forget type name? Oh, I guess I did. Put it back there now. It stops complaining. That's how I know when to add it. And that's what your queue should be for adding it to. If it complains about you not putting type name there, put it there. Does that make sense? So I make a vector of whatever types are contained inside of this container, and then I reserve to pre-allocate the space so that things go a little bit faster. And then for each sample that I need to get, well, I randomly pick something inside the container, right? That gives me an iterator back. So I dereference my iterator again to get the value, and so I add that value to my list of values. And then at the end, I can give that back. Any questions here? Yes. Again, reserve just pre-allocates the space, so it's going to make num samples worth of space inside my vector. This is just going to make the pushbacks go faster because the vector won't have to resize itself so often. Any other questions? Pushback adds the element to the end of the vector. So finally, we have another function over here where we want to make a random vector of some size, and the random values need to be between min and max. So again, because I know I'm going to need to be of some certain size, I reserve that much space to make things go faster. Then for each one of those elements that I need to generate, I get a random integer between the min and max, and I add it to the end of my random numbers. So I just have a vector of random values. The dot where? Oh, this one? So this is the pushback method defined on the vector up here. So random numbers is my vector, so vector.pushback. If you've done like list in Python, right, you've done like list.append or list.insert, pushback is the append of vectors. Any other questions? Container is not a keyword, no. Back up here, container is a variable. He's right over here. Any other questions? Okay then, we will continue on. The next thing that I want to show you is the algorithm library. There aren't any slides on it because I couldn't think of anything good to say, but we'll go over and we'll look at algorithm. Sorry. So algorithm is a set of generic functions that you will probably find very useful to use. I'd recommend looking at the algorithm page in the header file over here on c++.com to see everything that's there. For example, we have functions that will test if all of the elements in some range are some value, or are any of them meet some condition, or do none of them meet some condition. You might also want to apply a function to every element inside of a range. And you're going to see in our examples in a minute that most of these functions in algorithm operate on like a pair of iterators. Where do you want to start at? Where do you want to end at? So you can try to find a value. You can try to count how many occurrences of a value are there. You can try to find the first occurrence of a value that meets some condition. You can test whether like these two ranges are identical, or you can test whether these two ranges contain the same values potentially in different orders. You can copy some values. You can copy some values, but only if some condition is met. Copy only the ones that you want. You can swap two ranges. You can apply a function to transform all of the elements into a range to be something different. You can replace a particular value with some other value. Again, replace certain ones if some condition is met. You can remove elements from a vector if there's some value. You can remove them. You can remove some elements if they meet some condition. Some things you might also find useful are sorting. Okay. Right, so you can sort the elements in some range. Or you can test whether things are sorted or not. It also has min and max. So I'll show you some examples of using the library, and then we'll keep on going with things. Tomorrow, my plan for what we're going to cover is to cover namespaces, and then just do examples and review and see if you guys have any questions or things you'd like to review before next week we get into object-oriented programming. I know, right? Finally, 4 weeks in, or like 3 weeks in, we finally get to talk about OOs, what you're learning about in this class. I know, there's just a lot to cover to get you set up before you're ready for that. So, for example, here is a function that I'm going to use that's going to tell you whether all of the elements are negative or not negative. So here I use all of. I want to start at the beginning of my vector, and I want to go to the end of my vector. And I want to figure out if they're all negative. And you can see over here I have this function negative that returns true if the number is less than 0. Right? So I'm applying this function pretty much to every element inside the range to see if all of them are that value. It will stop, though, at the first one that's not that thing, so you do know that's sufficient. So any of, right, we'll start at the beginning of the vector, we'll go to the end, and we want to see if, any of the elements are negative. You guys have any questions about all of or any of? Yeah. What do you mean? So negative is the name of this function right here. So you don't want to use the parentheses here. We're not planning on calling the function right here. What the type of negative is actually a pointer to a function. So this is like the address of this function over here, which is what all of wants. So if you're using like all of or any of or like find if, you don't want to call the function. You just want to pass it in. For those of you guys that did Python, did you ever write functions that made other functions? Okay. Did you ever write functions that were like passed to something like map or apply? Okay. Then this all seems new. But you can totally do that in Python. Any other questions about all of or any of? So if we pop back over here, the first thing that I do is I do the all of and the all of on nums and on negative nums, and then I do the any of on nums. So do you expect all of the numbers in here to be negative? No, so we're going to say they're not all negative. For this one, we expect them to be all negative. So over here, right, we say that not all of the elements in here are negative. All of them are negative because they happen to be. Are any of the numbers in nums negative? Yeah, some of them are negative. So over here, this function over here, it finds the first element that matches this value inside of this range. So find the first value or the first element in this range that matches this value. And it's going to give you an iterator to that element. If it equals this guy over here, that means it didn't find the thing you're looking for. So if it's equal to the end, there are no values in that range that equal that value. But if it's not equal to the end, right, or whatever this argument happens to be over here, we will have found the first one at some position. And I use this function over here, distance, which is also defined in iterator, to figure out how far apart these two things are. What's the distance between the beginning and the iterator? So that gives me back a number. Yes? It returns an index, right, or like the number. So it's the distance between the beginning and where this iterator is at. So if the iterator had to go like 3 elements in, we'd do like, you know, the distance between 3 elements past the beginning and the beginning, which would be 3. I also have another function over here called absolute less than that just returns true if the absolute value of A is less than the absolute value of B. Over here, I do sorting. And so I just say, hey, sort the elements in that range. And notice again that I accept a copy of the vector because I wanted to keep the original outside and main, so I didn't change it here. But this will actually sort the vector in ascending order by default. What you can do, though, is you can pass another function in here, and it will sort it using that function. So here I'm going to sort by absolute value instead of supporting by numeric value. So if we go back here, right, so the first occurrence of 55 is at index 2, 0, 1, hey 2, there's 55. There aren't any negative 11s in here. When I did the sorting based on value, right, if we sort this range of numbers, we get negative 1, negative 55, negative 3, negative 2. Looks sorted, right? But over here, I sorted by absolute value. So I get negative 2, negative 3, 25, 25, 36, 53, 55, 55, negative 55. Again, these guys are all considered to be equal. 98 and then negative 100. Because if you sorted them by absolute value, that's what you'd get in ascending order. Does that make sense? Okay. The one that is really probably going to get you is remove. So I want to show you that before we leave today. And also, I used using intvec as std : vector of integers. So what you want to do if you want to remove all occurrences of a particular value from an array, you would do std : erase, no, remove. And then we say, well, we want to remove everything from the beginning of vec to the end of vec. And we want to remove all occurrences of this value. Now, if you go and you look at the documentation, it does not actually make our vector any smaller. The elements, it's still the same size, but what it will do is it'll erase all of those elements and kind of like move them to the end of the vector. But now that stuff at the end of the vector is very undefined as what's there. What this will give you back is an iterator to the new end of your vector. So now if I want to resize to actually only contain the elements that are supposed to be in there, I would do vec dot erase and I want to erase everything from that iterator, which is my new end, to the old end. So to kind of give you like an example of what's happening, let's say this is our set of numbers. So after we erase these numbers, what remove does is it kind of rearranges your list to be like this: 35, 25, assuming we were erasing the 12s, 16, 12, 12, 12, right? We're removing 12s. And what it's going to do is it's going to give you an iterator back to this position right here, the 16. Does that make sense? Then I say erase. I want to, I shouldn't say, it doesn't give it to the 16. It gives you the iterator to this first 12 here. Then we want to say, well, now I want to erase everything from where you gave me back this position to my end. So then it deletes it to become 35, 25, and 16. So the remove does this. The erase shrinks it down. Questions on that before we leave? Yes? What if you wanted to have 112 instead of removing them all? You just wanted to remove the first 12?
Do iterator plus 1 and then you have 1 instance.
I'm not sure if there's a way of using, there is a way of using remove if to accomplish what you wanted to do, but doing it is a little bit more complicated than you would expect. If you want to, you can come talk to me right now and we can discuss what you'd have to do to make that happen. But I will see you guys all on Friday.